take you to this practice quiz for today. Write the Taylor polynomial of order n. I've started it out for you. Suppose x represents time, and the present time is x equal a. We are projecting out into the future. So, p sub n of x is equal to...
Do you have like a little picture of a turtle like hovering, and it says the people looking for it is clearly unavailable? And then I checked the people that also have the page, and it said the same message.
Yeah, let me mute it. Okay. And okay. So we give you a little bit of time with this. And if you haven't worked on this homework, this won't come so readily, but think it through. See if you can get at least a little bit of this. Alright, so if we follow the pattern here, what would come next? This had no derivative. This is the first derivative. This is the second derivative. This is also going to have x minus a. And it's going to have, this had it to the 0th power, so you didn't have to write x minus a. This had it to the first power. This has it to the second power. But this is less important than this. They get progressively less important. This one was really divided by 0 factorial, which is 1, divided by 1 factorial, divided by 2 factorial. Third derivative, evaluated a over 3 factorial, x minus a cubed plus ... Keeps going, following the pattern. Now, this will make some sense if we think of x as being slightly in the future. Suppose x is slightly larger than a, just into the future. So we're saying, all right, we have the data up until the present time, and we go just into the future. Well, what do we expect f to be? Well, what it is now, at the present time. Plus, well, if it's increasing, then now, but this, if we go 1 unit into the future, then we'd multiply by f prime. But if we go just, 1/100th into the future, remember the derivative is the change in the output every time the input increases by 1. So if we just went 1/100th into a future, we just multiply the derivative by 1/100th, as we've done in practice quizzes. And then what we get is something that would correct for suppose our function had been doing this, and then when we follow the first derivative, it corrects for, not just taking the present height out, but for looking at the most recent trend. And then next we'd want to correct for, hey, this is concave up. So if you use the second derivative, but again, this is going to have a smaller effect. We have smaller and smaller effect, and the more that we go out on this polynomial. The main thing is this. The next main part is this, and then, with smaller and smaller corrections as we move on out. All right. Give me a little bit of feedback on number 1. Are you seeing the picture with the Taylor polynomial? Is it coming back from yesterday? A little bit of feedback. Or the day before yesterday. Yeah, it's very new information. Okay, so yeah, this factorial stuff, that was, when we look back at the Taylor polynomial, these things getting bigger and bigger. Now, let's look at this. If we replace if we just go to the nth power, then it's the Taylor polynomial of order n. If we stopped here at the nth power, that's what we'd have. But if we keep going out forever, then it's not the nth order, it's the Taylor polynomial period. And the Taylor polynomial period doesn't have this n in it. It's just p of x is this. And then it's the Taylor polynomial. And, all right. Now, let's go through some examples where we put it to use. Suppose you want to estimate, I'm going to need a little more space here. Square root of 26 using a fourth order Taylor polynomial centered at x equal a, where f of x equals square root of x. Choose an appropriate value for the center a. Right. Let me give you a moment to think about this. The function is the square root of x. We want to project out a little bit from a known value. Well, we know the square root of 25. So what we would do is we could say f of x equals the square root of x is the same as x to the 1/2. F prime of x is 1/2 x to the negative 1/2. F prime prime of x is negative 1/4 x to the negative 3/2. F triple prime of x. Multiply these, negative times negative is positive 3/8 x to the negative 5/2. Let's just go to the third derivative. So let's go with third order. And we would choose a being 25. This is really emphasizing how we tend to use the Taylor polynomial. we would not use f, the Taylor polynomial p3 of x centered at 0. This would be, if it was centered at 0, it would be f of 0 plus and come back up here and look at this, f prime at 0, x minus 0. Now if we did this, so on. Now this would having us project out 26 units away from our base position. And so the x is 26 larger than the 0. And the derivative way back, now this actually might work, but we'd have to go out a huge number of terms to get accuracy on this. And we don't tend to do this. This is not how we use Taylor polynomials do. Instead, we do p3 of x centered at something close to it where we know the value of it, of 25. F of 25 plus f prime at 25, x minus a, x minus 25, plus f double prime at 25, x minus 25 squared, and this is over 2 factorial, plus, we'll do just to the third order, f triple prime at 25 over 3 factorial, x minus 25 cubed. Alright, so what's happening here then is, give it a little more space. Now, how do I get these values at 25? Well, f of 25 is 25 to the 1/2, which is 5, square root of 25. F prime of 25 is 1/2 times 25 to the negative 1/2. Now, that's 1/2. 25 to the 1/2 would be 5, but negative throws it in the denominator. Okay, f double prime of 25 is negative 1, 4. Now, 25 to the negative 3/2. Negative exponent throws it in the denominator. The half is the square root of 25. 25 cubed, or 5 cubed, is 125. 1 over 4, 500. And f triple prime, 25 is 3/8 times 25 to the negative 5/2. And when you take it to the negative exponent, it puts it in the denominator. Square root of 25 is 5, 5 to the 5th. So big, I'm just going to leave it like this. 3 over 8 times 5 to the 5th. Alright, so then, what we're getting is, if we plugged all these things in, p3 of x would be f of 25 is, we said that's 5. F prime of 25 is 1/10 times x minus 25. F double prime of 25 is negative 1 over 500 times 1/2, because 2 factorial is just 2, times x minus 25 squared. And then the triple prime is 3 over 8 times 5 to the 5th times 1/6, because 3 factorial is 3 times 2 times 1, which is 6, times x minus 25 cubed. So we get this giant thing right here. Now, all it asks us to do, the answer to this question, choose an appropriate value for the center A. The answer is this simple. We would choose A to be 25, a known value. But I went above and beyond with this problem, and I'm actually constructing the Taylor polynomial of order 3 for this. Now, let's actually do, let me change to black. Now that I've constructed the Taylor polynomial of order 3, let's evaluate it at 26. Let's see what we get. Now, I want to show you a graph so we can kind of see it graphically as well as working it out. Graphically, the square root of x is this function that looks like this. When you're at 25, you know you're at a height of 5. Okay, so P3 of 26, which is really estimating the square root of 26, but not the square root of 26 exactly, but the square root of 26 with the Taylor polynomial. This polynomial of order 3, I think, is going to give us a pretty good approximation of the square root of 26. And the square root of 26, we can see, is going to be really close to 5. We should use 5. And we can also view this kind of like projecting into the future. Suppose the present time is t equals 25, or x equals 25. And we had the data right at 25. And we want to see, well, what's going on in the future? Well, to project into the future, you'd use the present value, but then you'd want to use the slope as well. And the slope, it looks almost 0. It's pretty flat, but the slope is actually 1/10. So that means if we went to the right 1, we'd go up 1/10 if we stayed along the tangent line, on the tangent line. And actually, when you substitute 26, we are going to go exactly to the right 1 unit. And so we should go up 1/10. But that's if we stayed on the tangent line. Now, if we stayed on the tangent line, the tangent line is going to be a slight overestimate. So we need to correct for that. And this corrects for us. The next thing is we'd use the slope, the second derivative, at 25, which is its concave down. And so we get minus, when you put these two together, minus 1/1000th times 26 minus 25 squared, plus, and then this one turns out to be 1 over here as well. We plug in our 26 right here. And now let's check this out with the calculator. I'm going to take the square root of 26. Square root of 26, according to my calculator, it is 5.099019514. Now, when I do this stuff, this is going to be 5 plus, and this is going to be 1/10 times 1, so it's 0.1. But notice 5 plus 0.1 is a little bit of an overestimate. It's on that red line. This is going to be a correction factor for us. Minus 1, now this 1 squared is just still 1. So minus 1/1000. And so when we do that, we wind up coming a little bit below this. We correct a little too much right here. If you put these three things together, so far this is 5.1 minus 0.001. And these three together would be giving me 5.099. Now, that's a bit of an underestimate. We went too far under. The next term is going to correct for that. And it's going to be plus this thing. And if I did all that, now this is going to reduce so I'm going to get, and that cubed is going to be 1, because 26 minus 25 is 1, 1 cubed is still 1. So it's 1 divided by, in parentheses, 5 to the 5th times 8 times 2. And it's plus 0.0040. And 2. And you see that if we put all these together, there's going to be this plus that 5.0992, which is slightly too big. No, 4 zeros. So we got to put another 0 in between there. 0, 2. And it was just slightly too big. And then the next term will correct for that, and so on. And you see how quickly this convergence series is going to converge on the correct answer. We don't have to go out very many terms because we used a value of a that was fairly close to this. You used the one that we knew the square root of, which was square root of 25. Now in actuality, we wouldn't use a Taylor polynomial for the square root of x, because the square root of x, we can just punch in our calculators and it's much quicker. But this demonstrates the point about how a Taylor polynomial gets used. All right, so when you're doing the homework, it's going to be problems that are kind of similar to what I just did right over here. Like here's one of them, f of x is square root of x, same function again. And when you're going to approximate 3.9, you don't have to use one that's smaller than that. You can use the closest one, which is 4, and then you might think of your delta x then as negative 0.1. and this will work great. And so it would be the same kind of thing to do this very next one. All right. And approximations with Taylor polynomials. You might have something like this. Approximate the Taylor polynomial with n equals 3. What you would do on something like 33 is you would say f of x equals e to the x. And then you would figure out what f prime of x was. Well, that's just e to the x again, and so on. F double prime. And then you would use a known value here would be use a equals 0. And then you know what e to the 0 is. And so you could do number 33 with that f of 0, f prime of 0. And you're going to wind up getting 1s for each one of these. And then you could build up your Taylor polynomial with n equals 3. This would be the same. Taylor polynomial starts out the same. This right here, but we'd plug in our a being 0, so it would wind up being looking something like the one that we crossed out up here. All right, give me a tiny bit of feedback here. Did this stuff make some sense? I picked out the homework problems that were not too difficult, that were somewhat like what I've shown. If you have an infinite Taylor problem, does it matter where it's centered around? In theory, no, it doesn't. But in practice, yes. Because what we want to do is only have to go for a couple terms and plug things in. So you want to pick your a very close to what the value is that you're going to be estimating a little bit later. So now if you're replacing it for a function in general everywhere, there are times we do that and we work in the theory. But when we use it to approximate values, we extend out just a little bit of ways from where we're at. All right. So that's as much as I wanted to go into today, and that'll get you ready for the homework. The homework is 11.1, and that's due at the final exam, and the final exam is on Monday, December 7th, and the exam today and the final exam, these are don't use your textbook, don't use your notes, don't use OneNotes. I did not put integrals where you needed formulas at the back of the book. So you're not allowed to use those formulas in the back of the book. Just the basic stuff is what you need. And the exam today will open up. Hang on just a second here. Do you want us to find the actual to compare it with the Taylor polynomial? Sure, that'd be very instructive. And all right, the exam today. Let me. If you go into the modules. 3 right here, and it is going to become available at 6:15, so you have a little bit of a break time, and then it's due at by 8:15 p.m. tonight. All right. Any questions?
Did you say we can use the formula on the back?
No, you cannot use the formulas in the back of the textbook. You don't need them. There's no tough integrals that need those formulas. Okay.
About the final exam, does it including before the midterm? We don't have midterm.
We never had a midterm. That is correct.
Oh, sorry. So about the final exam, it's including everything we learned in this class, right?
Yes, it is cumulative. It does cover everything in this class. Yeah.
Okay, thank you.
You're welcome. Okay, any other questions? All right, let me stop the recording.